This channel has been established for visually impaired people. For the visually impaired people, voice narration and a written expression are also provided for the hearing impaired. Don't forget to subscribe to our channel. Color American English or Color Commonwealth English is the visual perceptual property corresponding in humans to the categories called red, blue, yellow, etc. Color derives from the spectrum of light distribution of light power versus wavelength interacting in the eye with the spectral sensitivities of the light receptors. Color categories and physical specifications of color are also associated with objects or materials based on their physical properties such as light absorption, reflection, or emission. Spectra by defining a color space. Colors can be identified numerically by their coordinates because perception of color stems from the varying spectral sensitivity of different types of cone cells in the retina to different parts of the spectrum. Colors may be defined and quantified by the degree to which they stimulate these cells. These physical or physiological quantifications of color, however, do not fully explain the psychophysical perception of color appearance. The science of color is sometimes called chromatics, colorimetry, or simply color science. It includes the perception of color by the human eye and brain, the origin of color in materials, color theory in art, and the physics of electromagnetic radiation in the visible range, that is, what is commonly referred to simply as light. Contents 1 Physics of color 11 Spectral colors 12 Color of objects 2 Perception 21 Development of theories of color Vision 22 Color in the eye 23 Color in the brain 24 Non-standard color perception 241 Color deficiency 242 Tetrachromacy 243 Synesthesia 25 Afterimages 26 Color constancy 27 Color naming 3 Associations 4 Spectral colors and color reproduction 5 Additive coloring 6 Subtractive coloring 7 Structural color 8 Mentions of color in social media 9 Additional terms 10 See also 11 References 12 External links and sources Physics of color Continuous optical spectrum rendered into the sRGB color space The colors of the visible light spectrum Color wavelength Interval frequency Interval red approximately 700 to 635. Approximately 480 to 510. Thz. Mu m-1 EeVe. Kj mol-1 infrared. Orange 620,484,161,200,193 Yellow 580,572,172,214,206 Green 530,566,189,234,226 Blue 470,638,213,264,254 Violet 420,714,238,295,285 Near ultraviolet 300 1000 333 415 400 Far ultraviolet Appearance or apparition by Isaac Newton in 1671 include all those colors that can be produced by visible light of a single wavelength only, the pure spectral or monochromatic colors. The table at right shows approximate frequencies in terahertz and wavelengths in nanometers for various pure spectral colors. The wavelengths listed are as measured in air or vacuum. See refractive index. The color table should not be interpreted as a definitive list. The pure spectral colors form a continuous spectrum, and how it is divided into distinct colors linguistically is a matter of culture and historical contingency. Although people everywhere have been shown to perceive colors in the same way, a common list identifies 6 main bands: red, orange, yellow, green, blue, and violet. Newton's conception included a 7th color, indigo. Between blue and violet it is possible that what Newton referred to as blue is nearer to what today is known as cyan, and that indigo was simply the dark blue of the indigo dye that was being imported at the time. The intensity of a spectral color, relative to the context in which it is viewed, may alter its perception considerably. For example, a low-intensity orange-yellow is brown, and a low-intensity yellow-green is olive-green. Color of objects. The color of an object depends on both the physics of the object in its environment and the Characteristics of the perceiving eye and brain. Physically, objects can be said to have the color of the light leaving their surfaces, which normally depends on the spectrum of the incident illumination and the reflectance properties of the surface, as well as potentially on the angles of illumination and viewing. Some objects not only reflect light, but also transmit light or emit light themselves, which also contribute to the color. A viewer's perception of the object's color depends not only on the spectrum of the light leaving its surface, but also on a host of contextual cues, so that color differences between objects can be discerned mostly independent of the lighting spectrum, viewing angle, etc. This effect is known as color constancy. The upper disk and the lower disk have exactly the same objective color, and are in identical gray surroundings. Based on context differences, humans perceive the squares as having different reflectances, and may interpret the colors as different color categories. See checker shadow illusion. Some generalizations of the physics can be drawn, neglecting perceptual effects for now. Light arriving at an opaque surface is either reflected specularly, that is, in the manner of a mirror, scattered, that is, reflected with diffuse scattering, or absorbed, or some combination of these. Opaque objects that do not reflect specularly, which tend to have rough surfaces, have their color determined by which wavelengths of light they scatter strongly, with the light that is not scattered being absorbed. If objects scatter all wavelengths with roughly equal strength, they appear white. If they absorb all wavelengths, they appear black. Opaque objects that specularly reflect light of different wavelengths with different efficiencies look like mirrors tinted with colors determined by those differences. An object that reflects some fraction of impinging light and absorbs the rest may look black but also be faintly reflective. Examples are black objects coated with layers of enamel or lacquer. Objects that transmit light are either translucent, scattering the transmitted light, or transparent, not scattering the transmitted light. If they also absorb or reflect light of various wavelengths differentially, they appear tinted with a color determined by the nature of that absorption or that reflectance. Objects may emit light that they generate from having excited electrons, rather than merely reflecting or transmitting light. The electrons may be excited due to elevated temperature incandescence, as a result of chemical reactions chemoluminescence, after absorbing light of other frequencies, fluorescence or phosphorescence, or from electrical contacts as in light-emitting diodes, or other light sources. To summarize, the color of an object is a complex result of its surface properties, its transmission properties, and its emission properties, all of which contribute to the mix of wavelengths in the light leaving the surface of the object. The perceived color is then further conditioned by the nature of the ambient illumination, and by the color properties of other objects nearby, and via other characteristics of the perceiving eye and brain perception. This image, when viewed in full size, 1000 pixels wide, contains 1 million pixel, each of a different color. The human eye can distinguish about 10 million different colors. Development of theories of color vision. Main article, Color Theory. Although Aristotle and other ancient scientists had already written on the nature of light and color vision, it was not until Newton that light was identified as the source of the color sensation. In 1810, Goethe published his comprehensive theory of colors, in which he ascribed physiological effects to color that are now understood as psychological. In 1801, Thomas Young proposed his Trichromatic Theory, based on the observation that any color could be matched with a combination of three lights. This theory was later refined by James Clerk Maxwell and Hermann von Helmholtz. As Helmholtz puts it, the principles of Newton's law of mixture were experimentally confirmed by Maxwell in 1856. Young's theory of color sensations, like so much else that this marvelous investigator achieved in advance of his time, remained unnoticed until Maxwell directed attention to it. At the same time as Helmholtz, Ewald Hering developed the opponent process theory of color, noting that color blindness and afterimages typically come in opponent pairs: red-green, blue-orange, yellow-violet, and black-white. Ultimately, these two theories were synthesized in 1957 by Hurwitz and Jameson, who showed that retinal processing corresponds to the trichromatic theory, while processing at the level of the lateral geniculate nucleus corresponds to the opponent theory. In 1931, an international group of experts known as the Commission Internationale de l'Éclairage developed a mathematical color model, which mapped out the space of observable colors and assigned a set of 3 numbers to each color. In the main article, Color Vision normalized typical human cone cell responses S, M, and L types to monochromatic spectral stimuli. The ability of the human eye to distinguish colors is based upon the varying sensitivity of different cells in the retina to light of different wavelengths. Humans being trichromatic, the retina contains 3 types of color receptor cells, or cones. One type, relatively distinct from the other two, is most responsive to light that is perceived as blue or blue-violet, with wavelengths around 450 nanometers. Cones of this type are sometimes called short wavelength cones, S. Cones, or blue cones. The other two types are closely related genetically and chemically. Middle wavelength cones, M cones, or green cones are most sensitive to light perceived as green, with wavelengths around 540. Understimulated, leaving only the signal from the rods, resulting in a colorless response. Furthermore, the rods are barely sensitive to light in the red range in certain conditions of intermediate illumination. The rod response and a weak cone response can together result in color discriminations not accounted for by cone responses alone. These effects, combined, are summarized also in the Kruithof curve, that describes the change of color perception and pleasingness of light as function of temperature and intensity. Color in the brain. Main article, Color Vision. The visual dorsal stream green and ventral stream purple are shown. The ventral stream is responsible for color perception, while the mechanisms of color vision at the level of the retina are well described in terms of tristimulus values. Color processing after that point is organized differently. A dominant theory of color vision proposes that color information is transmitted out of the eye by three opponent processes, or opponent channels, each constructed from the raw output of the cones: a red-green channel, a blue-yellow channel, and a black-white luminance channel. This theory has been supported by neurobiology, and accounts for the structure of our subjective color experience. Specifically, it explains why humans cannot perceive a reddish-green or yellowish-blue, and it predicts the color wheel. It is the collection of colors for which at least one of the two color channels measures a value at one of its extremes. The exact nature of color perception beyond the processing already described, and indeed the status of color as a feature of the perceived world, or rather as a feature of our perception of the world, a type of qualia, is a matter of complex and continuing philosophical dispute. Non-standard color perception. Color deficiency. Main article, Color blindness. If one or more types of a person's color sensing cones are missing or less responsive than normal to incoming light, that person can distinguish fewer colors and is said to be color deficient or color blind. Though this latter term can be misleading, almost all color deficient individuals can distinguish at least some colors. Some kinds of color deficiency are caused by anomalies in the number or nature of cones in the retina. Others, like central or cortical achromatopsia, are caused by neural anomalies in those parts of the brain where visual processing takes place. Tetrachromacy. Main article, Tetrachromacy. While most humans are trichromatic, having three types of color receptors, many animals, known as tetrachromats, have four types. These include some species of spiders, most marsupials, birds, reptiles, and many species of fish. Other species are sensitive to only two axes of color or do not perceive color at all. These are called dichromats and monochromats respectively. A distinction is made between retinal tetrachromacy, having four pigments in cone cells in the retina, compared to three in trichromats, and functional tetrachromacy, having the ability to make enhanced color discriminations based on that retinal difference. As many as half of all women are retinal tetrachromats. P. 256. The phenomenon arises when an individual receives two slightly different copies of the gene for either the medium or long wavelength cones, which are carried on the X chromosome. To have two different genes, a person must have two X chromosomes, which is why the phenomenon only occurs in women for some of these retinal tetrachromats. Color discriminations are enhanced, making them functional tetrachromats. Synesthesia. In certain forms of synesthesia, ideesthesia, perceiving letters and numbers. Grapheme color synesthesia, or hearing musical sounds. Music color synesthesia will lead to the unusual additional experiences of seeing colors. Behavioral and functional neuroimaging experiments have demonstrated that these color experiences lead to changes in behavioral tasks and lead to increased activation of brain regions involved in color perception, thus demonstrating their reality and similarity to real color percepts, albeit evoked through a non-standard route. Afterimages. After exposure to strong light in their sensitivity range, photoreceptors of a given type become desensitized for a few seconds after the light ceases. They will continue to signal less strongly than they otherwise would. Colors observed during that period will appear to lack the color component detected by the desensitized photoreceptors. This effect is responsible for the phenomenon of afterimages, in which the eye may continue to see a bright figure after looking away from it, but in a complementary color. Afterimage effects have also been utilized by artists, including Vincent van Gogh. Color constancy. Main article, Color constancy. When an artist uses a limited color palette, the eye tends to compensate by seeing any gray or neutral color as the color which is missing from the color wheel. For example, in a limited palette consisting of red, yellow, black, and white, a mixture of yellow and black will appear as a variety of green, a mixture of red and black will appear as a variety of purple, and pure gray will appear bluish. The trichromatic theory is strictly true when the visual system is in a fixed state of adaptation in reality. The visual system is constantly adapting to changes in the environment and compares the various colors in a scene to reduce the effects of the illumination if a scene is illuminated with one light, and then with another, as long as the difference between the light sources stays within a reasonable range. The colors in the scene appear relatively constant to us. This was studied by Edwin Land in the 1970s and led to his Retinex theory of color constancy. It should be noted that both phenomena are readily explained and mathematically modeled with modern theories of chromatic adaptation and color appearance, e.g. CIECAM02, ICAM. There is no need to dismiss the trichromatic theory of vision, but rather it can be enhanced with an understanding of how the visual system adapts to changes in the viewing environment. Color naming. Main article, color term. See also, lists of colors and web colors. Colors vary in several different ways, including hue, shades of red, orange, yellow, green, blue, and violet, saturation, brightness, and gloss. Some color words are derived from the name of an object of that color, such as orange or salmon, while others are abstract, like red. In the 1969 study Basic Color Terms, Their Universality and Evolution, Brent Berlin and Paul K. describe a pattern in naming basic colors like red but not red-orange or dark red or blood red, which are shades of red. All languages that have two basic color names distinguish dark, cool colors from bright, warm colors. The next colors to be distinguished are usually red and then yellow or green. All languages with 6 basic colors include black, white, red, green, blue, and yellow. The pattern holds up to a set of 12: black, gray, white, pink, red, orange, yellow, green, blue, purple, brown, and azure. Distinct from blue in Russian and Italian, but not English. Associations. Individual colors have a variety of cultural associations, such as national colors in general described in individual color articles and color symbolism. The field of color psychology attempts to identify the effects of color on human emotion and activity. Chromotherapy is a form of alternative medicine attributed to various Eastern traditions. Colors have different associations in different countries and cultures. Different colors have been demonstrated to have effects on cognition. For example, researchers at the University of Linz in Austria demonstrated that the color red significantly decreases cognitive functioning in men. Spectral colors and color reproduction. The C. 1931 color space chromaticity diagram. The outer curved boundary is the spectral or monochromatic locus, with wavelengths shown in nanometers. The colors depicted depend on the color space of the device on which you are viewing the image, and therefore may not be a strictly accurate representation of the color at a particular position, and especially not for monochromatic colors. Most light sources are mixtures of various wavelengths of light. Many such sources can still effectively produce a spectral color, as the eye cannot distinguish them from single wavelength sources. For example, most computer displays reproduce the spectral color orange as a combination of red and green light. It appears orange because the red and green are mixed in the right proportions to allow the eye's cones to respond the way they do to the spectral color orange. A useful concept in understanding the perceived color of a non-monochromatic light source is the dominant wavelength, which identifies the single wavelength of light that produces a sensation most similar to the light source. Dominant wavelength is roughly akin to hue. There are many color perceptions that by definition cannot be pure spectral colors due to desaturation or because they are purples, mixtures of red and violet light, from opposite ends of the spectrum. Some examples of necessarily non-spectral colors are the achromatic colors black, gray, and white, and colors such as pink, tan, and magenta. Two different light spectra that have the same effect on the 3 color receptors in the human eye will be perceived as the same color. They are metamers of that color. This is exemplified by the white light emitted by fluorescent lamps, which typically has a spectrum of a few narrow bands. While daylight has a continuous spectrum, the human eye cannot tell the difference between such light spectra just by looking into the light source. Although reflected colors from objects can look different, this is often exploited, for example, to make fruit or tomatoes look more intensely red. Similarly, most human color perceptions can be generated by a mixture of 3 colors called primaries. This is used to reproduce color scenes in photography, printing, television, and other media. There are a number of methods or color spaces for specifying a color in terms of 3 particular primary colors. Each method has its advantages and disadvantages depending on the particular application. No mixture of colors, however, can produce a response truly identical to that of a spectral color, although one can get close, especially for the longer wavelengths, where the C. 1931 color space chromaticity diagram has a nearly straight edge. For example, mixing green light 530 Spectral colors cannot be matched exactly. However, natural scenes rarely contain fully saturated colors, thus such scenes can usually be approximated well by these systems. The range of colors that can be reproduced with a given color reproduction system is called the gamut. The C-chromaticity diagram can be used to describe the gamut. Another problem with color reproduction systems is connected with the acquisition devices, like cameras or scanners. The characteristics of the color sensors in the devices are often very far from the characteristics of the receptors in the human eye. In effect, acquisition of colors can be relatively poor if they have special, often very jagged, spectra caused for example by unusual lighting of the photographed scene. A color reproduction system tuned to a human with normal color vision may give very inaccurate results for other observers. The different color response of different devices can be problematic if not properly managed. For color information stored and transferred in digital form, color management techniques, such as those based on ICC profiles, can help to avoid distortions of the reproduced colors. Color management does not circumvent the gamut limitations of particular output devices, but can assist in finding good mapping of input colors into the gamut that can be reproduced. Additive coloring. Additive color mixing, adding red to green yields yellow, adding all three primary colors together yields white. Additive color is light created by mixing together light of two or more different colors. Red, green, and blue are the additive primary colors normally used in additive color systems such as projectors and computer terminals. Subtractive coloring. Subtractive color mixing, subtracting yellow from magenta yields red, subtracting all three primary colors together yields black. Subtractive coloring uses dyes, inks, pigments, or filters to absorb some wavelengths of light and not others. The color that a surface displays comes from the parts of the visible spectrum that are not absorbed and therefore remain visible without pigments or dye. Fabric fibers, paint base and paper are usually made of particles that scatter white light all colors well in all directions. When a pigment or ink is added, wavelengths are absorbed or subtracted from white light, so light of another color reaches the eye if the light is not a pure white source. The case of nearly all forms of artificial lighting, the resulting spectrum will appear a slightly different color. Red paint, viewed under blue light, may appear black. Red paint is red because it scatters only the red components of the spectrum. If red paint is illuminated by blue light, it will be absorbed by the red paint, creating the appearance of a black object. Structural color. Further information, structural coloration and animal coloration. Structural colors are colors caused by interference effects rather than by pigments. Color effects are produced when a material is scored with fine parallel lines, formed of one or more parallel thin layers, or otherwise composed of microstructures on the scale of the color's wavelength. If the microstructures are spaced randomly, light of shorter wavelengths will be scattered preferentially to produce Tyndall effect colors. The blue of the sky. Rayleigh scattering, caused by structures much smaller than the wavelength of light, in this case air molecules, the luster of opals, and the blue of human irises. If the microstructures are aligned in arrays, for example the array of pits in a CD, they behave as a diffraction grating. The grating reflects different wavelengths in different directions due to interference phenomena, separating mixed white light into light of different wavelengths. If the structure is one or more thin layers, then it will reflect some wavelengths and transmit others, depending on the layer's thickness. Structural color is studied in the field of thin film optics, a layman's term that describes particularly the most ordered or the most changeable structural colors. As iridescent structural color is responsible for the blues and greens of the feathers of many birds, the blue jay, for example, as well as certain butterfly wings and beetle shells. Variations in the pattern spacing often give rise to an iridescent effect, as seen in peacock feathers, soap bubbles, films of oil, and mother of pearl, because the reflected color depends upon the viewing angle. Numerous scientists have carried out research in butterfly wings and beetle shells, including Isaac Newton and Robert Hooke. Since 1942, electron micrography has been used, advancing the development of products that exploit structural color, such as photonic cosmetics. Mentions of color in social media. According to Pantone, the top 3 colors in social media for 2012 were red, 186 million mentions, accredited to Taylor Swift's Red album, NASA's landing on Mars, and red carpet coverage. Blue, 125 million mentions, accredited to the United States presidential election, 2012, Mars rover Curiosity finding blue rocks, and blue sports teams, and green, 102 million mentions, accredited to environmental friendliness, Green Bay Packers, and green-eyed girls. Additional terms. Color wheel, an illustrative organization of color hues in a circle that shows relationships: colorfulness, chroma, purity, or saturation. definition, how intense or concentrated a color is. Technical definitions distinguish between colorfulness, chroma, and saturation as distinct perceptual attributes and include purity as a physical quantity. These terms, and others related to light and color, are internationally agreed upon and published in the C lighting vocabulary. More readily available texts on colorimetry also define and explain these terms. Dichromatism, a phenomenon where the hue is dependent on concentration and/or thickness of the absorbing substance hue, the color's direction from white, for example in a color wheel or chromaticity diagram. Shade, a color made darker by adding black tint, a color made lighter by adding white value. Brightness, lightness, or luminosity, how light or dark a color is. See also. Find more about color at Wikipedia's sister projects. Definitions from Wiktionary. Media from Commons. Color portal. Chromophore. Color analysis. Art. Color mapping. Complementary color. Impossible color. International Color Consortium. International Commission on Illumination. Lists of colors. Compact version. Neutral color. Pearlescent coding including metal effect pigments. Primary, secondary and tertiary colors. References. Craig F. Boren 2006 Fundamentals of Atmospheric Radiation, An Introduction with 400 Problems. Wiley v. CHISBN. A. B. Judd, Dean B., Wischecki, Gunter 1975 Color in Business, Science and Industry. Wiley Series in Pure and Applied Optics. 3rd ed. New York, Wiley Interscience p. A. B. M. D. Fairchild, Color Appearance Models, 2nd ed., Wiley, Chichester 2005. Chart, Color Meanings by Culture, retrieved 29 June 2010. Mond, Barry. Color, Stanford Encyclopedia of Philosophy. Cyan, blue, indigo, purple, violet, magenta, white, gray, black. Color science. Color physics. Electromagnetic spectrum. Light, rainbow, visible spectral colors. Chromophore. Structural coloration. Animal coloration on vision and colors. Metamerism. Spectral power distribution. Color perception. Color vision. Color blindness test. Tetrachromacy. Color constancy. Color term. Color depth. Color photography. Spot color. Color printing. Web colors. Color mapping. Color code. Color management. Chrominance. False color. Chroma key. Color balance. Color cast. Color temperature. Eigengrau. Color psychology. Color symbolism. Color preferences. Lusher. Color test. Kruithof curve. Political color. National colors. Chromophobia. Chromotherapy. Color philosophy. Color space. Color model. Additive. Subtractive color mixing. Primary color. Secondary color. Tertiary color. Intermediate. Quaternary color. Quinary color. Aggressive color. Warm receding color. Cool pastel colors. Color gradient. Color scheme. Color tool. Monochromatic colors. Complementary colors. Analogous colors. Achromatic colors. Neutral. Polychromatic colors. Impossible colors. Light on dark tinctures. In heraldry. Color theory. Chromaticity diagram. Color solid. Color wheel. Color triangle. Color analysis. Art. Color realism. Art style. Color terms. Basic terms. Red, green.